Before proceeding any further with economics concepts, we'll spend some time reviewing some math that you'll need throughout this course and indeed throughout the rest of your econ studies. Most of this should be familiar to you already, and so you should have at least a working knowledge of how to apply the various tools because you will encounter them over and over again in the upcoming chapters. Much of economics centers around optimization problems. But for example, if you have a consumer maximizing utility or a firm maximizing profit. So I have a profit function, pi is equal to f of q. So this is a profit as a function of some quantity. Then the slope of this graph is going to be delta pi over delta q. That should guide the producer's decision. Why? Well, if this number is positive, that means that producing more is going to yield more profit. So I should produce more. If it's negative, the opposite is true. I would make more money by producing less, so I would be better off cutting back on output. Naturally, this means that at the maximized profit, so right here, the slope of the graph should be flat. Moving in either direction will reduce profit. This gives us the first order condition of optimization, which is that the slope of the objective function, so here that's the profit function, with respect to the choice variable, so that's the quantity, should be 0 at the optimum, which is here. If we take the limit of this slope, delta pi over delta q, as delta q goes to 0, then we get the derivative, which gives us the instantaneous rate of change of this function. And we could write this as d pi dq, or pi prime of q. The prime indicates a derivative. If I want to take the value of the derivative at a certain point, I would write pi prime of q1, or d pi dq evaluated at q is equal to q1. So the subscript indicates that we're evaluating the derivative at a specified value. If we want to state the first order condition, we can say that the derivative of the profit function evaluated at the optimum q star should equal 0. The first order condition is a necessary but not a sufficient condition for a maximum. So imagine if you have a parabola that's turned upside down, then the derivative is still going to be 0 at this point. Like, it's going to be flat. However, as you can clearly see, this is now at the bottom of the curve rather than at the top. So what we have here is a minimum and not a maximum. So the first order condition is satisfied both at a maximum and a minimum. So in order to distinguish between the two, we also need to check the second order condition. At a maximum, the graph should be concave down, or concave, as opposed to minimum, where it's going to be concave up, or convex. What this means is that the second derivative should be negative. If we look at the graph on the left, we can see that this graph is going to be concave up or convex. That means the second derivative is going to be positive, and so the critical point q star of a is a minimum, not a maximum. The third option we can have is that the second derivative is equal to 0, which would mean we have neither a maximum nor a minimum. So if we look at the graph on the right here, we see that at this point, the critical point is a point of inflection. The graph is going to switch from concave down to concave up, but it's not going to be a maximum or a minimum at this point. So if fq is equal to pi, then the second derivative can be written either as f double prime of q or d squared pi dq squared. So if you're curious about why the notation is different on the numerator compared to the denominator, think about this notation as applying the differential operators. The differential operator would be d dq applied to pi, and when you're taking the second derivative, you're applying this operator twice. So you have d squared pi dq squared. There's no pi squared. The second derivative is going to be negative at a local maximum and positive at a local minimum. And a graph can have many peaks and valleys. So we actually need to check all of these points to determine where our global maximum or minimum is going to be. So here are some common rules for derivatives. The derivative of any constant is going to be 0. Constants don't change. The derivative of any function, fx, multiplied by a constant a, is going to be the derivative of f prime of x, multiplied by that same constant. If we have a power function, such as x to the a, then we can use the power rule. So we bring down this a, and then we knock one power off the exponent. So the derivative of x to the a is ax to the a minus 1. The derivative of the natural log function is going to be 1 over x. And the derivative of a function a to the x is going to be a to the x log of a. So a special case of this is that if I take the derivative of the exponential function, log of e is just 1. So the derivative of the exponential function is just the same function. We also have some other rules. The derivative of a sum of functions is just a sum of derivatives. So f plus g prime is f prime plus g prime. To take the derivative of a product, we use a product rule, which says that fg prime is f prime times g plus g prime times f. And to take the derivative of a quotient, we use the quotient rule, which says that f over g prime is f prime times g minus g prime times f over g squared. If we have a composite function, y is equal to f of x and x is equal to g of z, so y is equal to f of g of z, we can find the derivative of that using the chain rule. So we would multiply the inner derivative g prime of z times the outer derivative f prime of x. Another way you can think about this is that dy dz is equal to dy dx times dx dz. Now, to be proper, we can't exactly just multiply and divide differentials as if they were any other variable. But for the purposes of understanding why the chain rule works, it's good enough. Here we have a couple examples of the chain rule at work. So for de to the ax dx, the outer derivative is just e to the ax, the inner derivative is a, so I have a times e to the ax. If I'm looking at the function log of a times x, the outer derivative is 1 over ax, the inner derivative is a, so the result is just 1 over x, which is the same as the derivative of log x, so the constant doesn't change anything here. In the third example, we're taking the derivative of log of x squared. So the outer derivative is 1 over x squared. The inner derivative is 2x. So it's going to give us 2 over x. We can also write this function as 2 log of x using the properties of the logarithmic function. And we can see that if we take the derivative of this, we get the exact same answer. So now let's take a look at a simple example. So let's say we have a profit function, pi is equal to 1000q minus 5q squared. Take the derivative, we use a power rule, so d pi dq is 1000 minus 10q. That's going to give us a critical point where this is equal to 0 at q star equals 100. That's the first order condition, but remember we always need to check the second order condition as well. The second derivative is just going to be minus 10. This function is actually concave everywhere, which means that the second order condition is going to be satisfied, and therefore this critical point is indeed a maximum. So far, we've just been looking at functions of a single variable, but in economics, we're often dealing with functions that take the prices or quantities of many different goods as inputs. So we need to have a firm grasp of multivariate calculus in order to conduct any meaningful analysis. We have a function y that takes many different inputs, x1, x2, all the way up to xn. Then we can take the derivative of y with respect to any single one of these variables. In order to do this, let's say we want to take the partial derivative of y with respect to x1. Then we would hold all of the other variables constant and only change x1. So we can either write this as del y del x1. So note that the partial derivative symbol is different from the normal derivative symbol. We can also write this as f subscript x1. This is nice because it takes up a lot less space. So if through the context it's clear what we're talking about, we can use subscripts, or we can simplify it even more and just write f1. So the partial derivative of f with respect to its first argument. Now, f1 can stand for a lot of other things too. So we're only going to use this when it's clear what we're talking about. In order to take the partial derivative of a function, we're going to treat all of the other variables as if they were constants and apply our usual rules. Let's say we have y is equal to ax1 squared plus bx1 x2 plus c x2 squared. So in this example, if we want to find del y del x1, we're going to treat x2 as if it were a constant. So this term, we would use the power rule, 2ax1. Here, x2 is just a constant, so we get bx2. So that's the partial derivative with respect to x1. We can get the partial derivative of x2 in the same way. We're going to treat x1 as a constant now. So this first term doesn't have x2 in it, so it goes away. This term is going to become bx1. The last term will become 2c x2. So in the second example, we have y is equal to e to the ax1 plus bx2. So if we want to take del y del x1, the outer derivative will just be the same function. And the inner derivative will just be a. If I want to find del y del x2, the outer derivative, once again, is the same function. The inner derivative is b. In the third example, y equals a log x1 plus b log x2. You can see that each variable appears in a separate term. So del y del x1 is just going to be in terms of x1. Del y del x2 is only going to be in terms of x2. One thing we can see from this example is that the logarithmic function is very useful because it can turn products into sums. And that simplifies partial differentiation by a lot because we can separate our variables into different terms and treat them separately. So what you'll see going forward is that we'll often be taking logarithmic transformations of complicated functions to simplify the math that we have to do when we're doing differentiation. One concept that shows up much more often in economics and in calculus courses is the notion of elasticity. So let's say we want to measure the sensitivity of a demand function, Q of P. So the quantity demanded as a function of price. And that would give us the partial derivative del Q del P. Now, by the ceteris paribus principle, we're holding all of the other variables constant. So the prices of all the other goods are treated as constant. So the partial derivative is going to measure the sensitivity of the demand function to the price. We can take the magnitude of the partial derivative, del Q del P, as a measure of how price sensitive the demand for this good is. However, just using the derivative by itself is a little problematic because both the price and the quantity are measured in certain units. The quantity is measured in bushels or barrels or pounds or whatever. The price is measured in some currency unit. So if we're trying to compare the price elasticity across different goods, that would be difficult. For example, if we wanted to compare oil and gold, well, the slope of the demand for oil is going to be measured in barrels. And therefore, we would have to figure out how much gold is equivalent to a barrel of oil if we want to make a direct comparison. That's pretty confusing. Elasticity is going to help us get around this problem because we are not going to look at the absolute change in each variable, but rather the proportional change. So the slope of a function would be delta y over delta x. Instead, what we're going to do is going to look at delta y divided by y over delta x over x. So the proportional response in y given a proportional change in x. This is useful because the units in the numerator and the units in the denominator are always going to cancel out. So this elasticity, epsilon yx, is going to be a unitless quantity. So we can compare the elasticities of different goods without having to worry about how the quantities are measured or how the prices are measured. A linear function, so y is equal to a plus bx plus other stuff, that's going to have a constant slope but not a constant elasticity. So elasticity here is going to be dy dx b times x over y. So b times x divided by a plus b of x plus whatever. If we look at this expression, we can see that as x becomes larger, bx gets large relative to the other terms. So this elasticity is going to be increasing, approaching 1 as x goes to infinity. If I have a power function, y is equal to a times x to the b, then the derivative is ab x to the b minus 1 times x divided by y. This is going to cancel out with this. This will cancel out with this. So the elasticity will be constant at v. This is even easier to show if we take a logarithmic transformation. So log y is going to be equal to log a plus b log x. And another way we can write the elasticity is it's going to be d log y over d log x. Well, if we look at this expression, d log y, d log x is just b. So returning to partial derivatives, we can define the partial derivative of y with respect to any of its arguments xi. We can also define the second partial of y with respect to any two arguments, xi, xj. So we can write this as fij. By Young's theorem, the order of differentiation doesn't matter. So it doesn't matter whether we take the derivative with respect to xj first and then xi, or the other way. So fij is equal to fji. We encounter second partials in economics quite a bit. So the own second partial, fii, that's the derivative of y taken with respect to xi twice. That's analogous to the second derivative of a univariable function. Whereas if I have fij and I and j are two different variables, that captures a lot of the interaction effects we'll be looking at. So going back to some of the examples we had from a couple slides ago, if we had this polynomial function, we have that f1 is 2ax1 plus bx2, and f2 is bx1 plus 2cx2. So if we want to find the second partials, f11 is the derivative of f1 with respect to x1. That's going to give us 2a. f12 is going to be the derivative of f1 with respect to x2. f21 is the derivative of f2 with respect to x1. And f22 is going to be the derivative of f2 with respect to x2. And we can verify here that Young's theorem indeed holds, right? f12 is going to be equal to f21. So it doesn't matter what order we take the derivatives in. For the function y equals e to the ax1 plus bx2, we have f1 and f2 here. So to find the second partials, f11, that's the derivative of f1 with respect to x1. We're just going to bring down another a. f12 is going to be a times b times the exponential term. f21 is also going to be the same thing. And f22, we're going to bring on another b. So we have our second partials here. In the third example, y is equal to a log x1 plus b log x2. The two terms are separable, so f1 is just in terms of x1, f2 is just in terms of x2. If f11 is minus a over x1 squared, f12 is equal to 0 because x2 doesn't appear here. f21 is also equal to 0, and f22 is minus b over x2 squared by the power of 4. When we're dealing with multivariate functions, the chain rule also gets a little more complicated. So let's say we have a function y, that's a function of x1 through x3, and each of these is a function of some parameter a. And let's say we wanted to find the total effect of changing a on y. We wanted to find dy dA. So here, the effect of a on y through x1, we can use the chain rule to get that. It's going to be del y del x1 times dx1 dA. But that's not going to be the only effect, because a is going to affect all three of the x's simultaneously. So the total effect is going to be given by this plus del y del x2 times dx2 dA plus del y del x3 times dx3 dA. So we can look at a special case where one of the x's is just the parameter a itself. Then in this case, the last term would simplify to the direct effect del y del a. And this is something we'll see a lot in this class, where we have a parameter a that influences some outcome variable both directly so del y, del a, and also indirectly through some other intermediate variables like x1 and x2. Now, suppose we have a function of multiple variables that's held at a constant value. So for example, let's say our total spending on a variety of goods is bound by some budget constraint. This is going to imply a relationship between the arguments of the function, right? If I have that my total spending is fixed, then buying more meat means that we can't afford as many vegetables. So I can think about the quantity of vegetables as an implicit function of the quantity of meat that I buy. Let's say I have an implicit function f of x1, x2 is equal to 0. It's always going to be 0 on the right-hand side because I could just move all the constants to the left-hand side. That allows us to define the implicit function x2 is equal to g of x1. Right? For any value of x1, there's a value of x2 that makes f equal to 0, and that's going to be how I define g. So what I can do is I can substitute g in for x2, so I have f of x1 and g of x1 is equal to 0. And I can differentiate this entire expression with respect to x1. So I have f1, and then for the second one, I want to use a chain rule. So I have f2 times g prime, that's going to be equal to 0. And g prime, if I rearrange, is going to be equal to minus f1 over f2. Remember, g prime was dx2 dx1. So if I had these two arguments, x1, x2, that were connected by this implicit function, then I can find the slope of the implicit function by taking minus the ratios of the partial derivatives f1 over f2. So how do we interpret this? Well, if I change one of these arguments, I need to change the other argument in order to keep the value of f at 0. The slope of this implicit function, g prime, is going to tell us if x1 changes, how much does x2 need to change by in order to keep us at f x1, x2 equals 0. So let's take a look at an example. Let's imagine I have 3 types of pizzas, x1, x2, x3, and the prices of these 3 pizzas just so happen to be p, 2p, and 3p. So they're all multiples of the same variable. Let's imagine that I have a consumer, and this consumer is going to spend $30 a week on each kind of pizza. So the demand functions are going to be x1 is equal to 30 over p, x2 is equal to 30 over 2p, and x3 is equal to 30 over 3p. We're going to let y be the total amount of pizza that they buy. So if I were to change the parameter p, that's going to affect the total amount of pizza through each of these 3 variables. Let's say we wanted to find dy dp using the chain rule. We can see here from y that the partial derivative with respect to each of the 3 arguments is just going to be equal to 1. So dy dp is going to be equal to dx1 dp plus dx2 dp plus dx3 dp, or minus 30 over p squared minus 15 over p squared minus 10 over p squared. So this sums up to minus 55 over p squared. This, not coincidentally, is the exact same answer we would get as if we were to just write y as a function of p. So we sum all that up, it's just going to be equal to 55 over p, and taking the derivative directly. One place where we can use the implicit function theorem is with the production possibilities frontier, like we looked at in the first chapter. Let's imagine we had a production possibilities frontier that was x squared plus y squared over 4 is equal to 200. And we wanted to find the slope of this guy. So I would have dy dx is equal to minus fx over fy. So the derivative of this thing with respect to x is 2x. The derivative with respect to y is y over 2. That's going to give us a result of minus 4x over y. What does this mean? If I have a production possibilities frontier that looks something like this, as I move down this curve, so as x increases and y decreases, the slope is going to get steeper and steeper. Once again, we can see that the implicit function theorem simplifies our calculation by a lot. We can get the same answer if we were to first write y as a function of x, and then take the derivative directly. So here, we would use the chain rule. So we have 1/2 over the square root of this guy times the inner derivative minus 8x. So 8 divided by 2 becomes a 4, so I have minus 4x. And this whole thing is just y. So I get the same answer whether I compute the derivative directly or if I use the implicit function theorem. But of course, this way is much easier. One thing that we'll see a lot is if I have a function that takes as its arguments one exogenous variable, a, and one endogenous variable, x. And we set that equal to 0. We can apply the implicit function theorem to see how changes in the exogenous variable a affect the value of the endogenous variable x. So we want to find dx dA, and applying the implicit function theorem, that's minus the partial derivative with respect to a over the partial derivative with respect to x. So for example, the first order condition for profit maximization says that price minus marginal cost equals 0. Here, price is the exogenous variable and quantity is the endogenous variable. If I apply the implicit function theorem, I get dq dp is equal to minus fp over fq. Fp is just 1, and fq is c double prime of q. This minus sign cancels out with that minus sign. And if we assume that the marginal cost is increasing, so c prime is increasing, meaning that c double prime is positive, then this whole expression is also going to be positive. What does that tell us? That tells us that the quantity supplied as a function of price is going to be increasing. So our supply curve is going to be an upward sloping curve. Now let's think about what we would do if we want to maximize a function of many variables. If we were to only vary x1 and hold all the other x's constant, then the change in y from x1 is going to be given by f1 times dx1. We want to maximize y with respect to not just x1, but all of the x's. So the first order condition is we're going to need f1 equals 0, f2 equals 0, all of the first partials to equal 0. The second order condition is a little bit more complex. Analogous to the single variable case, we would need all of the own second partials to be negative, but that's actually not enough. So we'll come back to that later. For example, let's take this function here, y is equal to minus x1 minus 1 squared minus x2 minus 2 squared plus 10. If we expand it out, it becomes minus x1 squared plus 2x1 minus x2 squared plus 4x2 plus 5. If we take the first partial derivatives, we have that del y del x1 is equal to minus 2x1 plus 2. So we want that equal to 0. That means that x1 has to equal 1. And del y del x2, that's going to be minus 2x2 plus 4 is going to be 0. So x2 star is equal to 2. Here, we don't actually need to check any second order conditions, because we can see what happens is that if we plug in these values, x1 is equal to 1 and x2 is equal to 2, that's just going to make the first two terms equal to 0. And in any other values, the first two terms will both be negative. So we know that x1 equals 1 and x2 equals 2 is going to maximize this expression. Now we're going to introduce one of the most useful and widely used theorems in all of economics. As we talked about already, most economic analysis is focused on how exogenous variables are going to influence endogenous variables. Let's imagine we have a function y is equal to minus x squared plus ax, where a is the exogenous variable, x is the endogenous variable, and we're choosing x to maximize y. So, if I were to change a, there's going to be two effects. There's going to be the direct effect of a on y directly, as well as the indirect effect, because changing a is going to tell me to choose a different value for x, and that's going to affect the value of y. If we look at this table, that's going to give us the optimized values of x star and y star for every value of a. So I look at each row. What I can see is in each row, y is going to increase by the midpoint between the current value of x and the previous value of x. So for example, when a increases from 3 to 4, y is going to increase by halfway between 3 halves and 2, or 7/4. So y goes from 9 over 4 to 16 over 4, or 4. The envelope theorem can be a little bit difficult to visualize, but if we have y is equal to minus x squared plus ax, then I can think about, for every value of a, I have a parabola y as a function of x. So this might be the parabola for a equals 0, I have another one for a equals 1, another one for a equals 2, and so on. And what I'm concerned about is the optimized values of x and y for each value of a. And the envelope theorem says I can just look at the upper envelope that connects all of these maximums. I don't need to worry about what's going on underneath. So let's think about how we would actually use the envelope theorem here. The direct method of finding dy dA is to first solve for x star as a function of a. So del y del x is equal to minus 2x plus a. So x star is equal to a over 2. If I plug that back in, I get y star is minus a over 2 squared plus a times a over 2. This all sums up to a squared over 4. And now I can take the derivative directly. dy star dA is just going to be equal to a over 2. In this particular example, finding dy dA directly is not that difficult. However, you can see that if the function were more complicated, this can get out of hand pretty quickly because solving this optimization problem can be difficult, and then plugging that solution into y can make it look really ugly really fast. The key intuition behind the envelope theorem is that if I want dy star dA, that's going to be equal to the partial derivative with respect to a plus the partial derivative with respect to x times the derivative of x star with respect to a. But since we're already optimizing y with respect to x, this term is going to equal 0 if we evaluate it at the optimum. What that means is that when the changes in the parameter a are small, this whole second term goes away. So we can ignore the indirect effect and look only at the direct effect. So dy star dA, the total derivative, is equal to the partial derivative evaluated at the optimum. So let's think about how that would work for our function here. The partial derivative del y del a is just equal to x. And then if we evaluate that at the optimum, that's going to give us a over 2. So we have that the total derivative dy star dA is just equal to a over 2. This is the same answer that we just got by computing this derivative directly, but when we use the envelope theorem, we did a lot less work to get there. The envelope theorem also works if I have a function that has multiple endogenous arguments. So I have n x's, and then I have this exogenous parameter a. If we're maximizing y, we have that the partial with respect to each xi is equal to 0, evaluated at the optimum. So we have that dy star dA is equal to the sum of all of these indirect effects plus the direct effect. And by the first order condition for optimization, all of these indirect effects are going to be equal to 0, which leave us with just the direct effect evaluated at the optimum, where each xi is chosen to be equal to xi star as a function of it. Let's take a look at an example of using the envelope theorem. So if we have a profit maximizing firm and their cost function is CQ equals 5Q squared, then the first order condition for profit maximization is P is equal to C prime of Q, which is 10Q. Or Q star is equal to P over 10. P is our exogenous variable here. If I plug this function, Q as a function of P, back into the profit function, the profit function is PQ minus C of Q. If I plug in P over 10 for Q, I get P times P over 10 minus 5 times P over 10 squared. That all sums to P squared over 20. And this will give me the result that d pi dp is equal to P over 10. But of course, I didn't need to do that. If I just use the envelope theorem, I can see that d pi dp is equal to the partial derivative evaluated at the optimum. The partial derivative is just q. If I evaluate that at the optimum, it's q star or P over 10. So once again, I get the same answer whether I compute this derivative directly or whether I apply the envelope theorem. But the envelope theorem saves us a lot of work.